In this exercise, we're going to find the area of the region of intersection of two circles using polar coordinates and double integrals. I'll demonstrate how to formulate the double integrals, and if you stick around until the end of the video, which I hope you will, I'll show you how to evaluate the double integrals. Suppose then we have two intersecting circles labelled here as circle 1 and circle 2. The region of intersection is shown in red. We are tasked with finding the area of the region shown in red. The equation of each circle is shown in Cartesian coordinates. Circle 1 has a radius of 2 and is centred at x equals 0 and y equals 2 and cuts the y-axis at y equals 4. Circle 2 has a radius of 2 and is centred at y equals 0 and x equals 2 and cuts the x-axis at x equals 4. The first step in finding the area is to convert the equations of each circle from Cartesian coordinates to polar coordinates. To do this, we'll substitute r cos theta for x and r sin theta for y. Making the substitution for x and y gives r squared into the bracket of cos squared theta plus sin squared theta minus 4r sin theta plus 4 is equal to 4. And using the trig identity where cos squared theta plus sin squared theta is equal to 1, we get r squared is equal to 4r sin theta. And dividing both sides of the equation by r gives r equals 4 sin theta. Now if we look at circle 2, in Cartesian form we have x minus 2 all squared plus y squared is equal to 4. And making the substitution for x and y gives r squared into the bracket of cos squared theta plus sin squared theta minus 4r cos theta plus 4 equals 4. And using the trig identity where cos squared theta plus sin squared theta is equal to 1, we have r squared equals 4r cos theta. And dividing both sides of the equation by r leaves r equals 4 cos theta. Now that we've found the radial distance r of each of the circles, let's look at the behaviour of r as we use it to compute the region shown in red. As r rotates in a counterclockwise direction from theta equals 0 to theta equals pi by 2, theta being the angle r makes with the x-axis, the radial distance from the origin is first determined by circle 1. When circle 1 intersects with circle 2 at some angle of theta, the radial distance from the origin is then determined by circle 2 until the area is complete. To find the angle of theta where the two circles intersect, we can set the polar equations of circle 1 to be equal to the polar equation of circle 2. The polar equation for circle 1 is r equals 4 sin theta, and for circle 2 we have r equals 4 cos theta. If we equate the two, we have 4 sin theta equals 4 cos theta. Dividing both sides of the equation by 4 and using the trig identity where the sine of theta divided by the cosine of theta is equal to the tan of theta, we're left with tan theta is equal to 1, and therefore theta is equal to tan to the minus 1 of 1. So in this case, theta is equal to pi by 4 radians. We are now in a position to start defining the limits of integration as r rotates about theta, which will be the outer integrals. The area of our region of intersection r can be defined as a double integral over the region r, where we sum infinitesimally small pieces of area shown as dA. In this case, the region, as we saw, is split into two distinct sectors, each represented by a double integral. In the first sector, theta started at 0 and continued to where theta was equal to pi by 4 radians. These form the limits of integration of the outer integral of our first double integral. We then saw that the second sector began where theta was equal to pi by 4 radians and continued to where theta was equal to pi by 2 radians, these forming the limits of integration of the outer integral of our second double integral. Now let's look at what happens when we sum infinitesimally small pieces of area along the radial distance r. This will help us define the inner integrals. This diagram represents a sector of the region capital R. The angle it makes is infinitesimally small and is denoted by d theta. Within the sector, we have infinitesimally small pieces of area denoted by dA. The size of each area is the length multiplied by the width. So in this case, dr is the length and r d theta the width. So dA is equal to r dr d theta. To find the total area of the sector, we integrate or sum in the r direction. In the first sector of area, when we sum or integrate along the radial distance r, we begin at the origin and travel along the perimeter of circle 1 until circle 1 intersects with circle 2. So we begin at r equals 0 and end at r equals 4 sine theta. In the second sector of area, when we sum or integrate along the radial distance r, we begin at the origin and travel along the perimeter of circle 2 until the area is complete. So we begin at r equals 0 and end at r equals 4 cos theta. Now we can add the limit of integration of our two sectors when we integrate or sum along the radial distance r. In the first sector, we saw that our lower limit was at r equals 0 and our upper limit was at r equals 4 sine theta. And in the second sector, we saw that our lower limit was at r equals 0 and our upper limit was at r equals 4 cos theta. In each of the double integrals, we are summing infinitesimally small pieces of area dA, which translates to r dr d theta. We can now start evaluating the double integrals. Beginning with the first of the inner integrals, we want to integrate between r equals 0 and r equals 4 sine theta r dr. Using the power rule, the antiderivative of this is r squared divided by 2, which we need to evaluate between 0 and 4 sine theta. And plugging in the value of r equals 4 sine theta gives 8 sine squared theta, and plugging in the value of 0 gives 0. So this integral evaluates to 8 sine squared theta. And for the second inner integral, we want to integrate between r equals 0 and r equals 4 cos theta r dr. And using the power rule to evaluate this, its antiderivative is r squared divided by 2, which we need to evaluate between 0 and 4 cos theta. And plugging in the value of 4 cos theta, we get 8 cos squared theta, and plugging in the value of 0 gives us 0. So this integral evaluates to 8 cos squared theta. And now moving on to the outer integrals. The first of these is the integral from theta equals 0 to theta equals pi by 4 of 8 sine squared theta d theta. And the antiderivative of this is 8 into the bracket of theta divided by 2 minus sine 2 theta divided by 4. And if you'd like to know how I evaluated the integral of sine squared theta d theta, please see this video here. And when we plug in the values of theta, this evaluates to pi minus 2. And for the second of the outer integrals, we need to integrate from theta is equal to pi by 4 to theta equals pi by 2, 8 cos squared theta d theta. And the antiderivative of this is 8 into the bracket of theta divided by 2 plus sine 2 theta divided by 4. And we need to evaluate this between pi by 4 and pi by 2. If you'd like to know how I evaluated the integral of cos squared theta d theta, please see this video. If we now plug in these values for theta, the integral evaluates to pi minus 2. So now we've evaluated our integrals. The only thing remaining to do is to add the constituent parts. So we have pi minus 2 plus pi minus 2. And this evaluates to 2 pi minus 4, which is our final answer.